Okay, so since I'm the only one here for the 2 p.m. GMT+2 meetup, I'll just continue on my own. I think we left off here, so I will continue this reading. The ability to parallelize computation has also contributed quite crucially to the progress in reinforcement learning. At least, check my sound. At least whenever simulation is an option. This has led to significant progress in computers achieving superhuman performance in Go, Atari games, StarCraft, and in physics simulation, e.g. using MuJoCo. See, for example, for a description of how to achieve this in AlphaGo. In a nutshell, reinforcement learning, I forgot to turn on screen sharing. So see, this was here, there's an example given to paper for the description of how to achieve superhuman performance in Go. In a nutshell, reinforcement learning works best if plenty of state action reward triples are available. Meaning whenever it is possible to try out lots of things to learn how they relate to each other. Simulation provides such an avenue. Deep learning frameworks have played a crucial role in disseminating ideas. The first generation of frameworks allowing for easy modeling encompassed Caffe, Torch, and Theano. Many seminal papers were written using these tools. By now, they have been superseded by TensorFlow, often used via its high-level API Keras. CNTK, Caffe2, and Apache MXNet. The third generation of tools, namely imperative tools for deep learning, was arguably spearheaded by Chainer, which used a syntax similar to Python NumPy to describe models. The idea was adopted of both PyTorch, the Gluon API of MXNet, and JAX. It is the latter group that this course uses to teach deep learning. So the latter group is a PyTorch, Gluon API of MXNet, and JAX. If I understood it correctly, JAX is like can almost be thought as a successor to TensorFlow. That might be wrong, or might be a bit off. Might be a bit off to describe it as a successor of TensorFlow. The division of labor between system researchers building better tools and statistical modelers building better networks has greatly simplified things. For instance, training a linear logistic regression model used to be a non-trivial homework problem, worthy to give to new machine learning PhD students at Carnegie Mellon University in 2014. By now, this task can be training a linear logistic regression model is the task. So training linear logistic regression models can be accomplished with less than 10 lines of code by now putting it firmly into the grasp of programmers. Chapter 1, Section 6, Success Stories. Artificial intelligence has a long history of delivering results that would be difficult to accomplish otherwise. For instance, mail is sorted using optical character recognition. These systems have been deployed since the 90s. This is, after all, the source of the famous MNIST and USPS sets of handwritten digits. The same applies to reading checks for bank deposits and scoring creditworthiness of applicants. Financial transactions are checked for fraud automatically. This forms the backbone of many e-commerce payment systems such as PayPal, Stripe, Alipay, WeChat, Apple, Visa, and MasterCard. Computer programs for chess have been competitive for decades. Machine learning feeds search, recommendation, personalization, and ranking on the internet. In other words, artificial intelligence and machine learning are pervasive, albeit often hidden from sight. It is only recently that AI has been in the limelight, mostly due to solutions to problems that were considered intractable previously. So here are a few examples given. In total, there are 5 examples given. So first example, intelligent assistance. First example for solutions to problems that were considered intractable previously. So first example, intelligent assistants such as Apple's Siri, Amazon's Alexa, or Google's Assistant are able to answer spoken questions with a reasonable degree of accuracy. This includes menial tasks such as turning on the light switches, a boon to the disabled, up to making barber's appointments and offering phone support dialogue. This is likely the most noticeable sign that AI is affecting our lives. Second example. Second example for solutions to problems that were considered intractable previously. A key ingredient in digital assistance is the ability to recognize speech accurately. Gradually, the accuracy of such systems has increased to the point where they reach human parity for certain applications. Third example, object recognition likewise has come a long way. Estimating the object in a picture was a fairly challenging task in 2010. On the ImageNet benchmark, Lin et al. 2010 achieved a top 5 error rate of 28%. By 27, Hu et al. 2018 reduced this error rate to 2.25%. So the error shrunk from 28% to 2.25% within 8 years on object recognition. So given pictures, detect what objects are seen in the picture. Similarly, stunning results have been achieved for identifying birds or diagnosing skin cancer. Fourth example, games used to be a bastion of human intelligence, starting from TD Gammon, a program for playing backgammon using temporal difference, abbreviated as TD, reinforcement learning. So I think there's one concept, temporal difference reinforcement learning. Algorithmic and computational progress has led to algorithms for a wide range of applications. Unlike backgammon, chess has a much more complex state space of set actions. Deep Blue beat Garry Kasparov, Campbell et al. 2002 using massive parallelism. Special purpose hardware and efficient search through the game tree. Go is more difficult still due to its huge state space. AlphaGo reached human parity in 2015 using deep learning combined with Monte Carlo tree sampling. So if I understood it correctly, the Monte Carlo tree sampling looks for a random option for a next move, and then given that next move, repeats it. So again, searches randomly for the next move, and repeats the process, repeats the process until a certain depth. And after repeating the tree sampling for multiple iterations, picks the move path that is providing the best value for the game outcome. And then I guess, well, I won't do guessing here, but okay, let's continue. The challenge in poker was that the state space is large and it is not fully observed. We do not know the opponent's cards. Libratus exceeded human performance in poker using efficiently structured strategies. Brown and Santon, 2017. This illustrates the impressive progress in games and the fact that advanced algorithms played a crucial part in them. Okay, fifth example for solutions to problems that were considered intractable previously. Another indication of progress in AI is the advent of self-driving cars and trucks. While full autonomy is not quite within reach yet, excellent progress has been made in this direction, with companies such as Tesla, Nvidia, and Waymo shipping products that enable at least partial autonomy. What makes full autonomy so challenging is that proper driving requires the ability to perceive, to reason, and to incorporate rules into a system. At present, deep learning is used primarily in the computer vision aspect of these problems. The rest is heavily tuned by engineers. Oh, I didn't know the last part. I thought they would be using deep learning in more areas of self-driving car engineering. But they say it's used primarily, so not only. So yeah, there might be other applications there. It would be interesting to know about the state of usage of deep learning in self-driving car engineering. Again, the above list barely scratches the surface of where machine learning has impacted practical applications. For instance, robotics, logistics, computational biology, particle physics, and astronomy owe some of their most impressive recent advances, at least in parts, to machine learning. Machine learning is thus becoming a ubiquitous tool for engineers and scientists. Frequently, the question of the AI apocalypse or the AI singularity has been raised in non-technical articles on AI. The fear is that somehow machine learning systems will become sentient and decide independently from their programmers and masters about things that directly affect the livelihood of humans. To some extent, AI already affects the livelihood of humans in an immediate way. Creditworthiness is assessed automatically. Autopilots mostly navigate vehicles. Decisions about whether to grant bail or use statistical data as input. More frivolously, we can ask Alexa to switch on the coffee machine. Fortunately, we are far from a sentient AI system that is ready to manipulate its human creators or burn their coffee. First, AI systems are engineered, trained, and deployed in a specific, goal-oriented manner, while their behavior might give the illusion of general intelligence. It is a combination of rules, heuristics, and statistical models that underlie the design. Second, at present, tools for artificial general intelligence simply do not exist that are able to improve themselves, reason about themselves, and that are able to modify, extend, and improve their own architecture while trying to solve general tasks. A much more pressing concern is how AI is being used in our daily lives. It is likely that many menial tasks fulfilled by truck drivers and shop assistants can and will be automated. I'm not so sure about that. Truck drivers and shop assistants, it's not like what is possible to automate right now. It's not like that is really the only thing that these um, that is like done when truck driving, for example, like a truck driver might also think about like the routes of the logistics company, and like what about this feedback of the hands-on experience of truck drivers combined with their opinions or their problems and their reasoning about it. Like, is that also plan of the of the roadmap? Or yeah, farm robots will likely reduce the cost of organic farming, but they will also automate harvesting operations. This phase of the Industrial Revolution may have profound consequences on large swaths of society. Truck drivers and shop assistants are some of the most common jobs in many states. Furthermore, statistical models, when applied without care, can lead to racial, gender, and age bias and raise reasonable concerns about procedural fairness if automated to drive consequential decisions. It is important to ensure that these algorithms are used with care. With what we know today, this strikes us a much more pressing concern than the potential of malevolent superintelligence to destroy humanity. I mean, a superintelligence would probably solve all these issues. Um, Summary, or chapter 1, section 7 summary. Machine learning studies how computer systems can leverage experience, often data, so the experience is often data, to improve performance at specific tasks. It combines ideas from statistics, data mining, artificial intelligence, and optimization. Often it is used as a means of implementing artificially intelligent solutions. As a class of machine learning, representational learning focuses on how to automatically find the appropriate way to represent data. This is often accomplished by a progression of learned transformations. Much of the recent progress in deep learning has been triggered by an abundance of data arising from cheap sensors and internet scale applications, and by the significant progress in computation, mostly through graphical processing units. Whole system optimization is a key component in obtaining good performance. The availability of efficient deep learning frameworks has made design and implementation of this significantly easier. Exercises. Which parts of the code that you are currently writing could be learned? Meaning improved by learning and automatically determining design choices that are made in your code. Does your code include heuristic design choices? I'm not writing any code at the moment. Which problems that you encounter have many examples for how to solve them, yet no specific way to automate them? These may be prime candidates for using deep learning. Viewing the development of artificial intelligence as a new industrial revolution, what is the relationship between algorithms and data? Is it similar to steam engines and coal? What is the fundamental principle? Where else can you apply the end-to-end training approach? Physics, engineering, econometrics. Okay. Um, Chapter 2, Preliminaries. To get started with deep learning, we will need to develop a few basic skills. All machine learning is concerned with extracting information from data. So we will begin by learning the practical skills for storing, manipulating, and pre-processing data. Moreover, machine learning typically requires a working with large datasets, which we can think of as tables where the rows correspond to examples and the columns correspond to attributes. Linear algebra gives us a powerful set of techniques for working with tabular data. We will not go too far into the weeds, but rather focus on the basic of matrix operations and their implementation. Additionally, deep learning is all about optimization. We have a model with some parameters and we want to find those that fit our data the best. Determining which way to move each parameter at each step of an algorithm requires a little bit of calculus, which will be briefly introduced. Fortunately, the AutoGrad package automatically computes differentiation for us, and we will cover it next. Next, machine learning is concerned with making predictions. What is the likely value of some unknown attribute given the information that we observe? To reason rigorously under uncertainty, we will need to invoke the language of probability. In the end, the official documentation provides plenty of descriptions and examples that are beyond this book. To conclude the chapter, we will show you how to look up documentation for the needed information. This book has kept the mathematical content to the minimum necessary to get a proper understanding of deep learning. However, it does not mean that this book is mathematics free. Thus, this chapter provides a rapid introduction to basic and frequently used mathematics to allow anyone to understand at least most of the mathematical content of the book. If you wish to understand all of the mathematical content, further reviewing section 80 should be sufficient. 18. Not 18. Okay. Chapter 2, Section 1, Data Manipulation. In order to get anything done, I will check if there's anyone who joined the meeting. Data manipulation. In order to get anything done, we need some way to store and manipulate data. Generally, there are two important things we need to do with data. First, acquire them, and secondly, process them once they are inside the computer. There is no point in acquiring data with some way to store it, without some way to store it. So let us get our hands dirty first by playing with synthetic data. To start, we introduce the n-dimensional array, which is also called the tensor. If you have worked with NumPy, the most widely used scientific computing package in Python, then you will find the section familiar. In MXNet, n the array is a class of any tensor n-dimensional array is a class, and any tensor n-dimensional array is an n-d array instance. MXNet's tensors are an extension to NumPy's tensors. N-dimensional arrays with a few killer features. The first MXNet's tensors support asynchronous computation on CPU, GPU, and distributed cloud architectures, whereas NumPy only supports CPU computation. Second, MXNet's tensors support automatic differentiation. These properties make MXNet's tensors suitable for deep learning. Throughout the book, when we say tensors, we are referring to MXNet's ND array instances, unless otherwise stated. Chapter 2, Section 1, Subsection 1, Getting Started. In this section, we aim to get you up and running, equipping you with the basic math and numerical computing tools that you will build on as soon as you progress through the book. Do not worry if you struggle to grok some of the mathematical concepts or library functions. The following sections will revisit this material in the context of practical examples, and it will sync. On the other hand, if you already have some background and want to go deeper into mathematical content, just skip this section. To start, we import the NumPy and NumPy extension modules from MXNet. Here, the NumPy module includes functions supported by NumPy, while the NumPy extensions module contains a set of extensions developed to empower deep learning within a NumPy-like environment. When using tensors, we almost always invoke the setNP function. This is for compatibility of tensor processing by other components of MXNet. A tensor represents a possibly multi-dimensional array of numerical values. With one axis, a tensor corresponds in math to a vector. With two axes, a tensor corresponds to a matrix. Arrays with more than two axes do not have special mathematical names. We simply call them tensors, algebraic objects here. To start, we can use a range to create a row vector x containing the first 12 integers, starting with 0. Though they are created as floats by default, each of the values in a tensor is called an element of the tensor. For instance, there are 12 elements in the tensor x. Unless otherwise specified, a new tensor will be stored in main memory and designated for CPU-based computation. Okay, so I'll try that out. think we'll go with an X not. This we have to install X not. Okay. We can access a tensor's shape, the length along each axis, by inspecting its shape property. If we just want to know the total number of elements in a tensor, i.e. the product of all of the shape elements, we can inspect its size property. Because we're dealing with a vector here, the single element of its shape is identical to its size. To change the shape of a tensor without altering either the number of elements or their values, we can invoke the reshape function. For example, we can transform our tensor X from a row vector with shape 12 to a matrix with a shape 3, 4. This new tensor contains the exact same values, but views them as a matrix organized as 3 rows and 4 columns. To reiterate, although the shape has changed, the elements in X have not. Note that the size is unaltered by reshaping. Okay. Reshaping by manually specifying every dimension is unnecessary. If our target shape is a matrix with shape, height, width, then after we know the width, the height is given implicitly. The height is given implicitly. Um, Reshaping. Ah, okay, because if there's fixed size, um, yeah, okay. Why should we have to perform the division ourselves? In the example above, to get a matrix with 3 rows, we specify both that it should have 3 rows and 4 columns. Fortunately, tensors can automatically work out one dimension given the rest. We invoke this capability by placing -1 for the dimension that we would like tensors to automatically infer. In our case, instead of calling x reshape 3, 4, we could have equivalently called x reshape -4, -1, 4, or reshape 3, -1. The empty method grabs a chunk of memory and hands us back a matrix without bothering to change the value of its entries. Okay. Okay. Typically, we will want our matrices initialized either with zeros, ones, some other constants or numbers randomly sampled from a specific distribution. We can create a tensor representing a tensor with all elements set to 0 and a shape of 2, 3, 4 as follows. Okay. Similarly, we can create tensors with each element set to 1 as follows. Often, we want to randomly sample the values for each element in a tensor from some probability distribution. For example, when we construct arrays to serve as parameters in a neural network, we will typically initialize their values randomly. The following snippet creates a tensor with shape 3, 4. Each of its elements is randomly sampled from a standard Gaussian um, parentheses normal distribution with a mean of 0 and a standard deviation of 1. We can also specify the exact values for each element in the desired tensor by supplying a Python list or list of lists. containing the numerical values. Here's the outermost list corresponds to axis 0 and the inner list to axis 1. Um, um, Switch to PowerPoint. Chapter 2, Section 1, Subsection 2, Operations. This book is not about software engineering. Our interests are not limited to simply reading and writing data from to arrays. We want to perform mathematical operations on those arrays. Some of the simplest and most useful operations are the element-wise operations. These apply a standard Scala operation to each element of an array. For functions that take two arrays as inputs, element-wise operations apply some standard binary operator on each pair of corresponding elements from the two arrays. We can create an element-wise function from any function that maps from a Scala to a Scala. In mathematical notation, we could denote such a unary Scala operator taking one input by the signature function mapping from real number space to real number space. This just means that the function is mapping from any real number R, a set of R, onto another. Likewise, we denote the binary Scala operator taking two real inputs and yielding one output by the signature function f, two inputs from real number space, outputting one number from the real number space. Given any two vectors, bold u and bold v, of the same shape and the binary operator f, we can produce a vector bold c equaling function uppercase f bold u bold v by setting um, c index I to output of function f of u index y and v index y. For all indices I, where c index I, u index I, and v index I are the ith element of vectors bold c, bold u, and bold v. Here we produce the vector valued function, uppercase F, mapping from two input vectors of dimensionality D from the real number space to one output vector of dimensionality D of the real number space by lifting the scalar functions. Lifting is by lifting the scalar function to an elementwise vector operation. The common standard arithmetic operators plus, minus, multiply, divide, and exponential have all been lifted to elementwise operations for any identically shaped tensors of arbitrary shape. We can call elementwise operations on any two tensors of the same shape. In the following example, we use commas to formulate a 5-element tuple where each element is the result of an elementwise operation. Okay. Equals towards tensor 1, 2, 4, 8. Y equals towards tensor 2, 2, 2, 2. So both tensors are vectors of dimensionality 4. Wait, I have to install torch. Okay. Fail building wheel for torch. Um, oh, it's not high torch. Okay, it's torch. As already installed. So x plus y, x minus y, x times y, x divided by y, x exponentiated by y. Not, describe exponentiation by words. Okay. Yeah, okay, makes sense. Many more operations can be applied in Elementwise, including unary operators like exponentiation. Um, uh, um, I'm actually not sure what like exponentiation means here. Um, is it, um, I don't think they mean squared, right? Um, um, it's probably yeah. So some mathematical constant E, Euler's number. Times exponentiated by the elements of the array. So 1, for example. Yeah, but it's the same as here 27183, 2718, rounded to 3. Okay. In addition to element-wise computation, we can also perform linear algebra operations, including vector dot products and matrix multiplication. We will explain the crucial bits of linear algebra with no assumed prior knowledge. That's good. In section 2.3, we can also concatenate multiple tensors together, stacking them end to end to form a larger tensor. We just need to provide a list of tensors and tell the system along which axis to concatenate. Okay, but the meeting is, I will wrap it up now. It's for scheduled to run for 1 hour. The next meeting is coming up at 4:30 p.m. GMT +2. Let me convert that to other time zones. So 4:30 p.m. That's 7:30 in San Francisco. 8 p.m. in India. 10:30 a.m. in New York. 11:30 in Argentina. And 10:30 p.m. in Hong Kong. All right. You can find the link to the meetups by going to 247 reading group. And then you can go to the meetup.com group. That's the first button or link on the 247reading.group website. And then you go to events. And then you'll see upcoming is 4:30 p.m. GMT+2. And once you sign up with Meetup and then RSVP for the meeting, you see the Zoom link. You can also directly obtain the Zoom link if you follow the second link of in the 247 reading group or HTTPS 247reading.group webpage, and you can go to progress of groups. It's a Google spreadsheet, and then you'll find the time here, which is for 16:30 or 4:30 p.m. in GMT+2, and see the link to the Zoom here. I think the meetup approach is more simple, but maybe you don't want to sign up for a meetup account or something like that. Okay.